Alright everybody, we're going to be waiting a couple minutes to get everyone in here. I can't wait to start. This is our first live stream. So excited. So we're going to wait a couple minutes and then we'll get right into it. Alright everybody. Let's put on some music. There we go. It's way better. Alright. Wait a couple more minutes to get people in. Alright, let's get right into it. So, I'm going to turn off the music so I can focus. Alright, so today what we're going to be doing is, as many as we can in an hour, we're going to be going through Project Euler, which is a coding challenge website. So I'm just going to be taking challenges from the website and then seeing how quickly we can solve them and how many we can get in an hour. So, let's get into the first coding challenge. I have it here. It is add all the natural numbers below 1,000 that are multiples of 3 or 5. Okay, so we have to add all the natural numbers below 1,000 that are multiples of 3 or 5. So what I'm thinking is we have something like a for loop, for I in range 1,000, right? For I in range 1,000, if I modulo 3 equals 0, which means it's a multiple of 0, or I modulo 5 equals 0, we say total sum equals total sum plus I. I'm gonna get the answers up here so that we'll be able to cross-check if I actually got it right. Okay. So we have to define total sum, obviously. We'll just define that as 0 for now. Let's see what we got here. Total sum equals 0 for I in range 1,000 if I modulo 3 equals 0 or I modulo 5 equals 0. Total sum equals total sum plus I. Looks like it's going to make sense. Let's run the code. Alright, let's run it. Save it up. We'll just save this as Euler for now. Let's see what it yields. Oh, we forgot to print. We forgot the print statement. So we'll just go print total sum. Let's see what we get. Run module. Okay, save it up. We get 233,168. Let me cross-check that with my answer. Yes, correct. Problem 1 solved. So I'm just gonna write here. I'll write down here. Alright, solved. Alright, what's the next one? The next problem is find the sum of all the even valued terms in the Fibonacci sequence which do not exceed, I'm spelling things wrong all over the place, 1 million. Which do not exceed 1 million. Okay. Alright, so the Fibonacci sequence, for you guys that don't know, the Fibonacci sequence is, it starts like 0 and then 1 and then 1 and then 2. So you're adding the last two numbers. So this would be 3, this would be 5, this would be 8, 13, 21, and so on. So what it wants us to do is it wants us to find the sum of all the even value terms in this which don't exceed 1 million. So I would think that we would have to start with for an iron range type of thing, but I don't know. I'm trying to figure out a way we can attack this. Let's start with a Fibonacci. Let's start with a Fibonacci sequence. So we'll go def fib, and then we can define x and y equals 0 and 1. Okay. Now, while true, we say yield x. And then we can say xy equals yx plus y. Right? Let's just call on it and see what happens. I'm just gonna comment out this code so we are not bothered by it. Alright, so let's say fib and the number 3. Let's run this. Run this model and let's see. Let's see what happens. Fib takes 0. Oh, right. It doesn't take an argument. My bad. Okay. Never mind. Now we need to find if the number is even. So let's do def sequence, and we'll say seq, seq, for a number in sequence if num modulo 2 we could say if not num, because if it's not going to be able to get remainder with 2, then we can just say yield that number. Yield num. Right? So that's that. Now, so we have our Fibonacci sequence, we have our defining whether it's even or odd, right? And now we have to figure out how to get it under 1 million, right? So we'll do another function called def 1 million, let's say, def 1 million. And we'll input the sequence. and we'll say for a number, for num in our sequence, if the number is greater than 1,000,000, how many zeros we have here? 100, 1,000, 10,000, 100,000, a million. A million will break. We will break. And then we'll just yield the number. Now all we have to do is call on these, so we'll just print the sum of the even numbers sequence. I guess I should call this even sequence so it's a little bit easier to understand. Even sequence, even sequence, fib. And our expected answer, let's see what our expected answer is. Checking the website. Okay, let's see what we get here. Running our, did we run our, okay, hold up, we need to run our module, and it's not printing for some reason. Did we do everything correctly? This is the issue, maybe we're running the wrong. Yeah, it's going to tell me that I need parentheses. Yeah, the syntax is invalid. Okay. Trying to figure out what we got here. This error that we have. For a number in our sequence. Alright, let's go through it again. This, I'm confident that this is our Fibonacci sequence, right? We have our even sequence for the number in a sequence. If it's not num divided modulo 2, then we yield our number. Then we have 1,000,000, and we say, we input the sequence for the number in the sequence. If the number is greater than 1,000,000, break, and then yield our number. And then we print the sum of the even sequence of the Fibonacci sequence. Okay. I see what we did here. We did not include the under 1,000,000 statement. So we have to do 1,000,000, parenthesis, add a parenthesis here, and now it should probably run. Do we need another? It should probably run perfectly. Let's check. Okay, we got the correct answer, right? So yeah, I just checked and we are completely good. So, great. On to the next one. I know we had a little bit of trouble with that, but that's perfectly fine. That's how it is. This is the first time me seeing these problems, so just bear with me. The next problem is we must find the largest prime factor of 3, 1, 7, 5, 8, 5, 8, 4, 9, 3, 1, 8, 0, 3. Okay. I just need to be reminded, what is a prime factor? What is a prime factor? Factor that is a prime number. Okay. I got it. Alright. So for example, okay, I understand. Okay, I'm not exactly sure how to attack this. Okay. Okay. Alright. Give me a second. I'm gonna try to understand. Alright. Okay. Alright. Let's start with a list. We'll just call it XS. Don't all quitters like calling their list XS. Alright. We'll put the number 2 in here. Because 2 can be divisible by itself and 1 as all other numbers. And we'll start with a prime function. So we'll go def primes. What we'll do with this function is that will define a minimum and a maximum. Okay? And these are preset functions in Python. So if 2 is greater than or equal to the minimum, we can say if 2 is greater than or equal to the minimum, we yield 2. And then we can say alright, let me just format this a little bit better. This is sloppy. And then we can say for I in range 3, which is the next number, the maximum, and 2, for P, for P in XS, we can say if I is divisible by P, or if I modulo P equals 0, or P times itself, or P times itself is greater than our I, we break. P times itself, sorry, caps lock on, is greater than I, we break. Okay. And then if I is divisible by P, if I is modulo P, list.append say xs.append I. Okay, so here we're actually trying to find what the prime factors are, right? So we start with like if 2 is greater than our minimum, then we yield 2. All right. So then 2 is our prime factor. For I in range 3, max 2, for P in our list, because for now it's 2 and XS, if I modulo P equals 0, or P times P is greater than I, do nothing. But if I modulo P, then XS appends I, so we have a new factor in that list. Alright? Now, so this just helps us find the primes, right? So we need to find the prime factors. So let's do a function factors with an input num. And then for the prime, for prime in primes, or 2 to that number, if our number is divisible with 0 remainder by our prime number, then we can say number just divide by prime and then yield our prime number. But if that number equals 1, then 1, you can divide 1 by anything, so we don't really care about that. Right? Alright. Now, all we have to do is just call upon it. So we'll say print the maximum factors of our number 317, 58, 49, 31803. Alright, just to re-explain what's going on here. Alright? I'm just gonna finish the parentheses so you guys can see what that looks like. Alright. What's going on here is that we start with this list with 2, which is the smallest possible factor that we can have. This is identifying and adding prime numbers to our list. This is identifying whether the prime numbers in our list are a factor of our huge number here. Okay? So if you guys have any questions, make sure to leave it in the chat. Obviously, I'll 100% be willing to answer you. Let me just check if you guys do have any questions. No? Okay. Let's get back into it. Alright. So what's the next question we have here? Next question we have. Alright, let's scroll down. Let's see. Alright, largest palindrome product. Largest palindrome. Hold on, I need to make sure that I'm spelling this right. Largest palindrome product. Alright. So, I'm just finding the full explanation here. Okay. Largest palindrome product. Boom. Alright. A palindromic number reads the same both ways. The largest palindrome made from the product of two two-digit numbers is 9009, and that equals 91 times 99. We are trying to find the largest palindrome made from two three-digit numbers. Okay. So this is the largest palindrome that can be produced from two-digit numbers. Now we're trying to find what is the largest product we can find out of three-digit numbers. I got it. Okay. I understand. Oh, that's my bad. Okay. So let's kind of just break this down, right? We need two numbers one number. In our case here, we need a number that ends with a 1 and some other constant, right? But with 3-digit numbers, it's not the same. Because 3-digit numbers, well, is it the same? Let's see. If we have for example, I don't know, 100, 101, or let's say the largest number, 991 times 999, what would that yield? 991 times 999. That would yield, that equals 990,009. So that does not work. So there's another factor here. There's another factor that we might have to consider. Okay. Well, we know 999 has to be, it just has to be the, it has to be one of the numbers, right? So let's go like this. I'm trying to figure out how we can attack this. I'm going to look up what the largest palindrome is. Alright, the largest palindrome is 906,609. Okay. Okay, I guess we need 999, and we need okay, we need the lowest value and the highest value, right? Okay, fine. So first we need to identify if it's a palindrome. So we'll do is palindrome with an input of a number. Alright, and then we return a string with that number, and if the string equals the number backwards, then it's a palindrome, alright? That's that. Then we have to find what the largest is. The largest palindrome. So we'll say the bottom value, bottom val, top val. I'm just making these variables extremely intuitive so you guys don't have any trouble understanding what's going on. So we'll say I equals 0, right? And for S in range but bottom val, or top val, -1, bottom val. Or actually, it should be top, bottom, -1. For Z in range this. If is palindrome, if is palindrome S times Z, if, and then we can say, sorry, if S times Z is greater than I then equals S times Z. And then we just simply return, I. And then we'll just run the function. So we'll say print largest. And we're going to input 100 because that's the lowest value you can possibly have. And we're going to have 999, which is the highest value we're going to possibly have. Close the parentheses. Okay, and let's see. Let me just extend our 3 commas here. Boom, 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 boom. Alright, let's see if this runs. And we get 906,609. Very nice. Very nice. Alright. So, now let's go to the next one. So we're going to, that was actually a pretty hard one, but the is palindrome one was not hard to understand. I mean, you just have to reverse it. That's not that much of an issue. It's just the fact that we had to do this whole function, which is a little bit of a pain. Yeah. But that's okay. It was fun anyways, right? We need to challenge ourselves during quarantine, during these times. Can't be sitting around and doing nothing all day, right? Okay. What is the next problem? Problem 5. We're just about halfway through. Alright. 2,520 is the smallest number that can be divided by each of the numbers from 1 to 10 without any remainder. The question is, what is the smallest positive number that is evenly divisible by all of the numbers from 1 to 20? Alright, so I'm forgetting to add t's here. 2,520 is the smallest number that can be divided by each of the numbers 1 to 10 without any remainder. Okay, so we're trying to find the smallest number that can easily be divisible by 1 through 20. Now if we multiply this by 2, it's not going to work, is it? Right? I don't think that's going to work. I'm checking with my calculator here. Yeah, that's just not going to work. Alright, okay. Alright, so we can say, we can go about it as follows. We can say our max range equals to 20. Where's my mouse? I'm going to go up because I don't want you guys to see the bottom the whole time. We're going to go up, 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 up. Way better. Okay. Our max range is equivalent to 20. Equivalent to 20. Now we need to check if, yes, div. We're going to check if a number can be divisible, can be divided. So we'll say for I in range 11 to 21. We could do range max. We'll do max range. Max range plus 1. That's 21. 21. If n modulo I equals 0, then we must continue on. Else No way. Return false. Can't happen. No way. So, if that can happen, then we return true. Now, I guess we can say now our number let's say our number is 2, right? While not, just hold on really quick, while not yes div, we're going to print the num. We're going to add 2. So this is going to give us, this is actually pretty simple, right? If you see here, well, it's not going to be divided by 2. Well, it's not divisible by any of these numbers in our range. We're going to add 2. Because here we don't need to account from 1 to 10, because if it's divisible by 10, it's divisible by, if it's divisible by 10, it's divisible by 20. If it's divisible by 5, it's divisible by 10. Or actually the opposite. I don't know, but there's a correlation, so we don't need to account for all 20 numbers. So I think we're set here. Let's run and see what we get. Save it up. Ah, I forgot the parentheses. I'm still living in Python 2. All good. I love parentheses. We will run. Beautiful. We're going to run for a long, long time. Let's see what we get. It's going to take a little bit. So while we're here, if you guys are not subscribed to the channel, make sure to subscribe. We'll be bringing more coding content, machine learning content. We love bringing content to you. Our schedule is going to be Wednesdays, regular post, Friday, live stream, Sunday, regular post. And we're going to be posting on our second channel very soon, so look out for that. And make sure to sub to the second channel. So yeah, let's wait for this to be ready to run. I think we can actually figure out a way to make this take less time. Alright, this is gonna take a while, so while we're waiting for this to run, right? And I want it to run it. You know, I have no problem waiting, so we can just go on to the next one, right? This is number 6. Pat yourselves on the back if you're still watching. Number 6, congratulations. You've come a long way. Okay. Number 6. Just check on idle here. It's going for a long time. That's okay. We'll check back on that in a couple minutes. Ah, this looks like a complicated one. The sum of the squares of the first 10 natural numbers is 385. So let me just visualize that for you guys. The sum of the squares of the first 10 natural numbers is so 1 squared plus 2 squared plus so on until 10 equals 10 squared equals 385. Now they're doing a little play on words. The square sum of the first 10 natural numbers, which is 1 plus 2 plus so on until 10, squared equals 325. 3025, my bad. 3025. Hence the difference between the sum of the squares of the first 10 natural numbers and the square of the sum is 3025 minus 385, which is 2640. Find the difference between the sum of the squares of the first 100 natural numbers and the square of the sum. Okay. So, alright. So first, let's do a sum squares function. This is not gonna be that hard. I'm surprised that this is the 6th problem. Other problems were a little bit harder for me, but alright. So we'll do sum of squares, right? Sum of squares. Sum of squares, and we'll input a number. And we'll now say, now we're going to say, so we have to get for I in range num, since we say sum of squares, the number is going to be the amount, like the final number. So we'll just say top num. So we can say, hold up. Just having a little issue with the Wi-Fi here, give me a second. Alright. Okay, never mind. Let's start again. We'll have a sum. We'll have x, alright? X equals 0. For I in range 101. Sum will equal sum plus I squared. Alright? And then we just print sum. That is sum squares. Now square sum also equals 0. For I in range 101, square sum plus equals I, and then we just print square sum, and we square it. Our final answer, let's scroll up for you guys. Our final answer would be square sum minus sum, or our x, and then we just print final answer. Oh, let's check on idle, right? Oh, it's still running. Okay. I think that should just be about it. So if we run, oh, missing parentheses to call print. Right. Print sum. Oh my god, I called on sum instead of x. My bad. So many sums here, sum square, square sum, whatever. Alright. We'll run the module. Oh my god, guys, I'm lacking here. I am completely lacking. It's alright. Missing parentheses all over the place. It's okay. There we go. Let me check if that's the right answer. Hey, it's the right answer. Okay. Well, looks like that's just about it for today. I think I'm gonna end the stream here. Thank you for everyone who was watching. I really appreciate it. By the way, I did not get the end number, but I compared it to the answer text on the website, and this code, the palindrome code, is correct. So don't, or not the palindrome code, the smallest number that can be divided by 1 to 10. This is right. So it just takes a while to run, and I'd run it previously, but this works. So don't worry about that not working. It just takes a little bit of time to compile. But besides that, thank you guys for watching. I really appreciate it. Have a nice day. Make sure to subscribe if you aren't already subscribed, and we'll see you on our post on Sunday.